Okay, now we're looking at how we can add damping to a machine in order to reduce the vibration. If you remember this curve from before, and you've already seen examples of it with our little beam inside iTeach Resonance, you can see that for different values of zeta, which we'll talk about in a second, with more damping we get less amplification. So when something's very lightly damped, we get a lot of amplification. When something's heavily damped, we get less and less amplification. In fact, we can even, have lower vibration at the natural frequency in these cases. But we talked about that in the dynamic section, so hopefully you feel fairly comfortable with this. The real point is, stiffness pushes it this way, mass pushes it this way, but damping just reduces the amplification effect of the resonance. And we did see this earlier, but I'll quickly just demonstrate it again. If I take my beam that I have here and I make it vibrate, what do I want to do there? Just make it vibrate. If I artificially add damping, I'm not changing the frequency, I'm just causing it to suppress the vibration. All that vibration is turned into energy, into heat instead of allowing the machine to vibrate quite so much. Now, for a lot of machines that you deal with a lot of structures, it's just not practical to add damping. But in certain circumstances it may be, or it will be, so you may even want to get consultants in who specialise in this field, or sell these types of products, and they can show you exactly where to put it. Now, there's dicing, I guess I should say, there's damping that we may add along a surface like this to suppress it, but there's also damping that we can put under the base of the machine to dampen the vibration that way as well. Also to isolate the machine vibration. But by adding lots of damping here, we've really suppressed the vibration. It's now not a problem if we could use this solution though. Now, this is a nasty looking equation, but what it's trying to show you is that zeta, which is the critical damping ratio, or the damping factor, is a ratio of the critical damping to the actual viscous damping that we're seeing. So the critical damping is that point at which we don't get any overshoot, where we excite it but we don't get any excessive vibration. Less than that and it's overdamped, below that and it's underdamped. So this is the equation. The key feature here is just to look at the critical damping over, the viscous damping, the actual damping in our situation as a ratio to our point at which it would be critically damped. And that's where this Q factor comes into it. The Q is basically the shape of the curve that we looked at before. Something with a high Q, or high quality factor, or high magnification factor, is going to have that high sharp peak as we just saw before. So if it's lightly damped, if there's very little damping, then it will amplify the vibration a great deal. If we then increase the damping, the Q factor will come down and we will have less vibration as a result. So here's our curves again. You can see where it's lightly damped, I have this 0.05. Where it's critically damped is this point where the damping ratio is 1. The way to calculate it is by looking at these half power points. So at what point is the amplitude on this curve equal to half the actual magnification that I'm getting? And you can see in this case it's always 0.707 the actual value. So if I look at the frequency at the lower point and the frequency at the higher point and look at that as a ratio, I get my Q factor. So for example, if my natural frequency happened to be 100 Hertz and I look at these half power points, or the point at which it's 0.707 of the value, then I can see that if these were wider apart, which they would be as I come down these curves. So for example, for this curve, the half power point might be out here and out here. So that frequency delta will be greater, which makes this value greater, which changes them as you can see here. So there's the theta value, which is the ratio of the viscous damping to the critical damping, and my Q factor. You can see as the frequency delta is increased, the Q factor is lower. So high Q means there's a lot of amplification, low Q means there's much less amplification. So you need to look at what sort of options you have for adding damping, and there are materials and products out there that can be used to add damping to a structure. Many are called viscoelastic. They are capable of storing the strain energy when deformed and dissipating a portion of this through hysteresis. Several types are available in sheet format, and I've got pictures or diagrams I should say in a moment. Some are adhesive, so they're glued onto the surface, and others are enamel-like for use at higher temperatures. So if you did have a flat surface, this rubber product that I'll show in a moment is laid down, is glued on top. So every time the machine's trying to vibrate, it's causing that to deform, and through this viscoelastic effect, it's dissipating the energy. So if the energy is dissipated that way, it will vibrate less. There's only so much energy there, so if part of it's lost in heat, then we don't get as much movement. There are a couple of types: this free layer or extensional damping and constrained layer damping. And I would suggest that if you were thinking about using a damping product, that you bring in people who sell it, and they can perhaps advise you on whatever the best type is. But you can see the damping material here. So just to quote, the free layer damping material, or free layer materials, are generally vinyls, which have platelet type fillers in them. So these are the little platelet fillets. As the material to which they are applied vibrates, the platelets slide against one another, and it's this friction between the platelets that converts the vibration energy into heat. So by dissipating it as heat, we get less vibration. You can see where this information has come from. So the machinedesign.com website for more information. These constrained layer damping systems, so the CLD, you can see it's just slightly different. If you look at the first one, there's just the layer, but in this case it's more like a sandwich. So a sandwich is formed by laminating the base layer to the damping layer and adding a third constraining layer. When the system flexes during vibration, shear strains develop in the damping layer. Energy is lost through shear deformation rather than extension of the material. So either way, it's trying to dissipate the energy as heat, thus dampening the vibration. Again, you need to look at where it's applicable. In some cases you might find that a machine is built inside an enclosure, and that enclosure has the damping material. So it might be loud inside the enclosure, but using the damping material on the enclosure itself, it stops the vibration from getting out to people working in the area or other machines and such. Okay, so thus far we've looked at a couple of methods for dealing with natural frequencies. Next we're going to, and high vibration for that matter of any sort, next we're going to look at tuned absorbers, which are designed to specifically tune out one of the natural frequencies.